You hear the term machine learning thrown around everywhere, but what does it really mean? In this explainer, we're going to pull back the curtain and show you the surprisingly human element that's at the heart of it all.
We have this image of computers just sort of absorbing data and magically getting smarter on their own. But that's not really how it works. The reality is way more intentional. In fact, you could say it all starts in a kind of classroom.
Yeah, exactly. Just like us in school, machines have different ways they can learn. And it all comes down to the kind of study materials we decide to give them. And there are really two main approaches.
Okay, so on one hand, you've got supervised learning. This is basically like learning with a cheat sheet. We give the machine a ton of data where every single thing is already labeled. This picture is a cat. This one is a dog. The whole point is for the machine to figure out the rules so it can label new pictures it's never seen before. Then you have the total opposite, unsupervised learning. Here we give it all the same photos, but we give it zero labels. We just say, go figure it out, find the patterns. The machine has to discover for itself how to cluster similar things together without us ever telling it what a cat even is.
Now, you might be thinking, okay, I get it. You pick a method, you throw the data in, and you're done, right? Well, not so fast. That's where most people miss the single most important part of this whole process. The real secret sauce isn't in the fancy algorithm. It's in how we prep the data for the algorithm.
And this is where we really get to the heart of it. Andrew Ng, he's a legend in this field, co-founded Google Brain. He put it perfectly. He said, applied machine learning is basically feature engineering. This is the hidden art, the human intuition that makes the difference between a model that's just okay and one that's truly incredible.
So what on earth is feature engineering? Well, think of it this way. It's the art of using your human expertise to choose, change, and even invent the best possible inputs or features for the model to learn from. It's all about helping the machine focus on what's actually important, cutting through all the noise to find the real signal.
It's all about giving the machine little hints. And one of the simplest but most powerful ways to do that is with something called an indicator variable. It's basically a simple yes or no flag that you add to the data.
Okay, let's make this real. Imagine you've got a bunch of data, and one column is just age, just a number. By itself, maybe not super helpful. But you, with your human brain, know that if you're trying to predict, say, who might buy a certain product, the age 21 is a huge deal, right? The legal drinking age. So what do? You create a brand new feature, a simple yes or no column called is_over 21. Boom. You've just given the model this massive clue it never would have found on its own.
But wait, there's more. It gets even cooler when you start combining features that already exist to create brand new ones that are way more powerful than the original parts.
For example, take marketing. You've got two numbers, how many people clicked an ad and how many people saw the ad. We call those impressions. They're okay on their own, but the real magic, it happens when you put them together. You divide the clicks by the impressions, and suddenly you have a click-through rate. This one new number you just created, it tells you how effective the ad is. That's so much more insightful than just the raw numbers.
But, and this is a huge but, all this creativity, all this engineering, it creates a fundamental problem, a real conflict that is at the very core of machine learning. Can a model be too smart for its own good or too simple?
This whole conflict really boils down to two types of error. First, you've got bias. That's the error you get when your model is too simple. It's called underfitting. It's like it's trying to draw a straight line through a curvy pattern. It just misses the point. Then, on the complete other end of the spectrum, you have variant. This is the error from being too complex. The model gets obsessed, I mean literally memorizes the training data, including all the random noise and mistakes. We call that overfitting. It looks brilliant on the test, but fails completely in the real world.
This target analogy nails it. The goal, the bullseye, is low bias and low variance. Perfect predictions every single time. Now, high bias, that's when you're super consistent, but you're consistently wrong. You keep hitting the same spot on the wall, way off target. That's underfitting. High variance, that's when your shots are all around the bullseye, but you never actually hit it. You're all over the place. That's overfitting. The whole game is to get as close to that bullseye as you can.
And this is what makes it a trade-off. It's a balancing act. See, as you make your model more complex to try and reduce that bias, you almost always increase the variance, and vice versa. They pull in opposite directions. The real art, the job of the human in the loop, is to find that perfect sweet spot right in the middle where the total error is as low as possible.
And this whole challenge, this balancing act, it's not new, not at all. It's the result of a really long journey of discovery that's been going on for decades.
I mean, think about it. The basic idea of an artificial neuron was cooked up way back in 1943. It took until the 80s for key ideas like backpropagation to really catch on, but then things started to accelerate, fast. 2012 was a huge year with breakthroughs in image recognition, which really kicked off the deep learning craze. And that leads us straight to things like ChatGPT popping up in 2022. Every single one of these steps was really about finding better ways to handle that bias-variance trade-off.
Okay, so let's tie this all together. What's the big takeaway? If these models are built on human choices, human-engineered features, and they're balanced on this razor's edge between being too simple and too complex, what does that actually mean for us, for society?
This is where the word bias takes on a second, really powerful and kind of chilling meaning. We're not just talking about a technical error anymore. We're talking about algorithmic bias. Because if the data we use to train these models reflects our own society's prejudices, and it does, the model will learn them, and worse, it'll amplify them. This opens up a whole can of worms, right? Who's responsible when a biased model makes a bad call? How can we even trust these black box models if we can't see how they work? It means the human choices we make during that feature engineering step have massive ethical weight.
So at the end of the day, machine learning isn't some neutral, objective thing happening in a server somewhere. It's a mirror. It reflects the data we give it and the human choices we make along the way. So the question we have to leave you with is this. If we are the guides, how do we make sure the models we build reflect the world we want to live in, and not just the one we happen to have right now?